So, we've talked about the Lagrange equations as far as conservative forces go. We have these two things. So nice to have two boards, with one plus in this one. Right. So we come to these equations in the case of a conservative force. We all know very well what conservative means. What we need at this point is a way of describing systems with more than one particle. Because we've come to describe things like a pendulum on a string, and particles with more than one degree of freedom, with more than one Lagrange equation. We've been able to express more than one potential energy. When we derived the equations of Lagrange, we did so for a system of particles. And we did so under the assumption that the following was true. When we derived these equations, we got an expression called T, which in our derivation was a sum over all the particles in the system of mass times velocity squared. That was the definition of T that we came across as we went from Newton's equation to the Lagrange equation. And that's the definition we must stick with. And what it means is when there's more than one particle in the system, the kinetic energy is simply the sum of all the kinetic energies of every individual particle in the system. When we then went and wrote out this equation, we derived a guy called U. We said that this was essentially a potential function from which all the forces are simply derivatives. Now, there's a result that I haven't shown you if this is in class yet. Yes, it should. Very good. So, we derived a result called U as well, and I didn't show this explicitly in class. Maybe for the people having an oral test tomorrow, they ask them in there. You can show in the same, as we did the derivation for this, we've got a value called U, we've got it in terms of the generalized forces, and when there's more than one particle, it's the sum of the potentials of each particle. Just like the kinetic energy is the sum of the kinetic energy. This is true for something like gravitational potential energy, or pretty much any potential energy. So, these two equations give us T and U for a system. And if we have T and U for a system, we have L for that system. And if we have L for the system, we can write down these equations, and we have the equation going into the system. This is very different from Newtonian mechanics. And I want to stress that Lagrange's equations and Newton's equations are equivalent. They are the same thing. We're not doing any new physics, we're not having any new fundamental assumptions. But the reason why I say this is very different from how we normally treat a mechanical problem is because we only need these two things, and we have everything. We don't have to look at every single particle in the system and take note and bookkeep every force acting on every particle in the system in order to solve its motion. Why is it a good thing? Well, how many particles are there in this podium? A bloody large number. There's a lot of particles in there. Millions, billions, trillions, 10 to 25, maybe 10 to 26. That's how many particles. Generally in classical mechanics, make the assumption that how this is so big, it's infinite. Well, who's going to sit working out the forces on every single one of those particles? And how they influence each other. And it's just going to be an act. In Lagrange mechanics, we only need to compute T and U, and we're done. Now, the astute student is really thinking, yeah, that's very nice, but for T and U, you need the velocity and the mass of every particle in the system anyway. So, you're just putting wool over our eyes. In fact, this is the same. You still need to go through every particle in the system in order to compute these values. Now, what we're going to do today is we're going to find fancy ways of getting these guys. We probably won't have time to find too fancier ways around these guys, but we'll certainly find fancy ways of generating this guy. Now, where to start? I think an appropriate place to start is with a really simple problem. We'll solve the problem using Lagrange equations, and I'll then leave a couple of open questions to go through with all tests soon. And by the way, I'm going to upload the test from last year. I think that's practice one for the test for this week. We're going to start with the following problem. Let's say I've got a system which is basically a particle here, a line, and a particle here. Right? Let's assume that this line is massless. We're not going to worry about it. We're going to think of these as two heavyweights sitting at each end of a seesaw. So, I think that's how you call it, seesaw. And there's two heavyweights going, right? It's doing its angular motion. It's allowed to spin around some pivot point. And let's choose the pivot point at some point along the seesaw. Now we're going to play a game. We're going to ask, given that I know how heavy this guy is, and given that I know how heavy this guy is, where must I place the pivot so that it balances? Where must I place this pivot so that if I start it out horizontal and at rest, it remains there? Okay. So let's do a survey. If I start out with 100 kilogram heavyweight on this side and 100 kilogram heavyweight on this side, where must I place the pivot? Halfway. Who says halfway? That's pretty clear. It's the choose of the odds. If I place the thing halfway, it'll balance. What if I now make this guy 200 kilograms? Must I go that way with the pivot or that way with the pivot? Who says this way? Okay, still pretty much majority. Who says this way? So, yeah, I'll get away. We must go closer to the heavier guy in order to compensate for the fact that he's heavy, right? So, you've seen often you've seen parents playing with their kids on seesaws, and the parent will sit much closer to the pivot point so that they have a fair seesaw ride, as opposed to if they stand at one end, in which case would just be like a clump, and the kids will be sitting on the top with nowhere to go. So it's a similar thing. We have to put it close to this side. Anyone can guess as to where exactly? Now you know that. 1/3 of the way along. 1/3 of the way along. Quarter of the way along. So who said a quarter? Who said a third? Ah, that's equal. Okay, so we have to find an answer to this question using mathematics. Because we don't know. I mean, is it a quarter of the way? Or is it a third of the way? Or is it 214,518ths of the way? What is the fraction that we must put this pivot at in order for the system to balance? So the way we're going to solve this is we're going to set up Lagrange equations for the general pivoting motion of the seesaw. Once we've got the general equation of the seesaw, we're going to ask what is the specific case of this in which it remains flat. And we're going to solve for where to place the pivot. let's do it. So we place the pivot at some distance d. So anyway, we place the pivot at some distance d from some reference point. Now reference point can be anywhere. In other words, let's call this pivot a general motion. Right, so now we've actually got an hour of relaxed real lecturing. Just under an hour. Let's have a look. In general, right, the system is pivoting around some point, somewhere, along its pivotal point here, right? And in general, when I don't necessarily require that it's balanced, it's allowed to pivot, it's allowed to move. And it's allowed to move in what we call the angle that it lifts at theta. So in general, this is the motion of the seesaw. It's pivoting around, moving up and down. Now, let's parameterize this. Let's say that the distance from the left end to that point, that distance that we were wondering about, is d. Right. Is d a generalized coordinate? Who says yes? Who says no? Who says what the hell is d anyway? So d is the distance, I'm specifying the distance from the left end point to the pivot is a thing called d, right? I'm trying to solve for the value of d that will make this thing balance. It is not a generalized coordinate because it's something that I fix and then I let the seesaw run. And then I may change it to another value and let the seesaw run. But any whilst the seesaw is running, it's not changing, right? So it's something externally controlled. Certainly physics is not changing the value of d. The thing is not allowed to slide up and down the pivot. It's fixed at this point throughout the duration of the motion of the pendulum. D is a parameter that I specify, distance to pivot from left end. It is not a generalized coordinate. How many generalized coordinates does the system have? One degree of freedom. What generalized coordinate can I choose? Theta. The angle that it is rotating at. So let's do that. The generalized coordinate is theta. That's 1 degree of freedom. And we can write down our transformation equations. Now we have two particles living in 2D space. How many Cartesian coordinates are there? There's the coordinates of this one, let's call them x1 and y1. And there's the coordinates of this one, let's call them x2 and y2. Right, so now we can write the transformation equations that give x1, x2, x1, y1, x2 and y2 in terms of theta, right? So let's say that the whole rod has a length L. So in that case, the distance from the pivot up the rod to x1 is L minus d. Right? This distance is L minus d. From there it should be quite clear what the equations of transformation are to get x1 from the pivot, right? Anybody guess? So L minus D cos theta, L minus D sin theta. What about x2 and y2? So d cos theta will be somewhere up here. We have to go minus d cos theta, right, to get down. So that. So here are our transformation equations. In order to proceed any further, we need to work out kinetic and potential energy. To work out kinetic energy, we first need to work out the derivatives of these guys. So we may as well work those out here. x1 dot is equal to L minus d is constant. Cos theta is not, however, so this looks like minus L minus d theta dot minus theta, and this looks like this one looks like L minus d theta dot cos theta, and this one looks like d theta dot sin theta, and this one looks like minus c theta dot theta. And finally, we can work out the kinetic energy of the system. The kinetic energy of the system, as we work up there, is simply a half, or it's the sum of all the kinetic energies of each of the particles. So it's going to be a half. Now, this one is m1 and this one is m2. To associate with x2, y2, and to associate with x1, y1, they each have different masses. We'll solve it for general masses m1 and m2, and then we'll consider the case when m2 is 200 kilograms and m1 is 100 kilograms to answer our quiz question from the beginning. So let's see. A half, this one is going to be m1 times by this squared plus this squared. I'll just write it down for now. x1 dot squared plus y1 dot squared plus a half m2 x2 dot squared plus y2 dot squared. Right. So what's this squared plus this squared? L minus d squared theta dot squared. Right? So this is a half m1 L minus d squared theta dot squared plus what's this squared plus this squared? That's d squared theta dot squared. A half m2 d squared theta dot squared. Right, so that is the kinetic energy of the system. What about the potential energy? Well, what are the forces acting on the seesaw? Gravity. There's tension, we don't care about it. We're doing Lagrange mechanics, we don't have to worry about it. So gravity is the force on the seesaw, and gravity has a potential energy which looks like mg height from reference. And we can write the potential energy of the first one is mg y1, mg height, m1 g height, plus the potential energy of the second one, yeah? M1. Yeah. It's sandwiched in there. And the height is y1. Plus, right, so the sum of the potential energies. Now we have all the ingredients we need to go ahead and write down the Lagrange equation for the system. So, that's convenient. Well, O is T minus U, which is, in this case, let's group all the terms in there. Looks like a half m1 m1 L minus d squared plus m2 d squared theta dot squared, that's the kinetic energy, minus the potential energy, minus m1g. y1 is what? y1 is L minus d sine theta. And y2 is minus d sine theta, so I'll just have plus d sine into d sine theta. Right, and I may as well group those terms as well. There's a sine theta in common between them. So I can right, I can group everything. So that's the Lagrangian system, and now we simply follow our noses and write down the Lagrange equation. Yeah. Yes, there is. Good. Let's put the G outside. I like doing my positive terms first, in fact, so I'm going to just rewrite this whole thing. Plus bracket. It's going to look like y2 d sine, no, just d minus m1 L minus d g times theta. Is that one okay? So there's the Lagrangian. Now we simply need to write down d by dt del Lagrangian by del theta dot is equal to del Lagrangian by del theta. The equation that is burned into your memories by now. So we simply write this out. What's the root of this thing with respect to theta dot? Well, the way I've written it out is quite nice. There's constants there and theta dot there, constants there and theta there. So we simply need to derive that. Well, that's easy enough. That's just going to be, I'm not skipping steps even though I could, d by dt of m1 L minus d squared plus m2 d squared dot is equal to, and L by del theta. Now we ignore this term, we just look at this one. That becomes a cos theta. And we're differentiating with respect to theta, not with respect to time, so nothing else happens. M2 d minus m1 L minus d g cos theta. Right, so let's take this time derivative, and what do we get? We get m1 L minus d squared plus m2 d squared. Dot is equal to this side. That'd be right. Right. So what's the point of this? We've learned the equation of motion. That's correct. What was our initial objective? It wasn't to the equation of motion, it was no. If we start things horizontal and with no initial angular velocity, when will they stay there? When I say start horizontal, what do I mean? Theta is 0. Theta naught. When I say with no initial angular velocity, what do I mean? Theta dot is 0. Right. So I can substitute theta. Double dot is the thing that I don't know the value of. But theta is something that I know to be 0. If theta is 0, it means cos theta is 1. So in my particular case of starting position, I have essentially This goes away, right? Becomes a 1, right? So I can solve for theta double dot in this case. What do I get theta double dot is equal to m2d minus m1 L minus d times g over the denominator m1 L minus d squared plus m2 d squared. Alright, now I know how the second derivative will look in the initial state. What do I want the second derivative to be? Do I want it to be moving? No. So I want the second derivative to be 0. If it's 0, it means it's not going to move because initially the velocity is 0, the position is 0. This is an important velocity is 0, it's not moving. And if this one was also 0, it would mean it will never move because it's not moving and its motion is not changing. Newton's law of the second order, if you've got two derivatives 0, then you find yeah. But essentially, it's a good question because actually when you go and you look macroscopically at everything in physics, there is no non-conservative force. No forces are really non-conservative. Friction is non-conservative because we're making huge approximations. Actually, it's a whole lot of electrostatic charges that we're collecting as well. Really, there are no non-conservative forces. Okay, so we want this to be 0. What is the denominator? The denominator is positive, negative, 0. Always positive. Mass is never negative, and these guys are squares. Right? Unless the length of the rod is 0, which is the point of the situation, the denominator is always positive. So if we're setting this whole thing to 0, we don't care about the denominator. It's never infinite. And it's always positive, so we can just neglect it. So making this equal to 0 implies that the numerator is 0. It implies that m2d minus m1 L minus d times by g if you like, but let's just divide through by g, is equal to 0. Okay, now we can solve for t, can't we? Now we have an equation, we're nearly at our answer. Let's solve for d. This implies that x group terms, I don't know the answer offhand, so I have to check it out. m2 plus m1 times by d is equal to m1L. Rearranging that. Right. And that implies that d is equal to m1L over m1 plus m2. Alright, let's go back and see what happens here. So we've got 100 kilograms and 200 kilograms. So in our case, m1, remember, is